Hi all. Today my group members and I would be presenting to you about temperature adaptive radiative coating for all season household thermal regulation. So we would be focusing on temperature radiative coatings, how it works, its properties and structure, its working principles, and more application of the materials would be discussed. The natural process by which an object emits heat energy in the form of infrared radiation or IR is known as radiative cooling. Using static cooling optimized material qualities, much emphasis has been placed on increasing the radiative cooling capacity of roof coatings on hot days. The invention of a mechanically flexible covering that adjusts its heat emittance to changing air temperatures was employed to establish a novel form of thermal regulation. The temperature adaptive radiative coating has many benefits compared to other traditional methods of radiative coating. Its sky window emittance is being adjusted automatically. As shown in the picture here, according to different temperature, the material adjusts itself during warm and cooling climates. In an exterior test environment, TARC displays efficient surface temperature regulation. TARC outperforms conventional coating materials of roof in order to save energy. The TARC's emittance switching allows for a wide range of cooling power radiation modulation in response to ambient temperature. TARC's emittance switching and temperature regulations were demonstrated in a 24-hour outdoor testing that was conducted in California on a summer day. In that test, the TARC was 2 degrees warmer than the other two reference roof coverings. And on a sunny day, the TARC's high sky window emission was EW equals to 2.0. And it also observed lower radiative cooling capacity than other references, whereby EW equals to 0.90. The TARC keeps rooftop temperatures nearer to heating and cooling set points.
I'm going to introduce about the structure and the properties and mechanisms of the TARC. The TARC is fabricated by the photolithography process, which is showing 7 steps here in the right set. And so it has very special structure, a lithographically patterned two-dimensional array of thin tungsten vanadium oxide blocks in a barium fluoride dielectric layer that sits on the top of a silver layer. So the structure, if we apply the TARC in the heavy-duty outdoor applications, the TARC should be protected from dust and moisture, which can use the thin polyethylene membrane to coat it on the surface of the TARC as shown in the figures here. And another alternative fabrication method is to using polymer imprinting, which is to embed the vanadium dioxide particles in the layer of polyethylene membranes. So due to the special properties of the tungsten vanadium oxide, TARC also has very special properties. The tungsten vanadium dioxide has a metal insulator transition temperature, which is around 22 Celsius degree. If temperature is lower than transition temperature, tungsten vanadium oxide will show insulating state. So the thermal emission of TARC is around 0.2. If the temperature is higher than transition temperature, the tungsten vanadium oxide will show metal state. The thermal emission will be of TARC will be 0.9. Because of the temperature change, if the temperature is lower than 22 Celsius degree, the tungsten vanadium dioxide is transparent to the infrared radiation. It is showing insulating state, and so the infrared it will be reflected by the silver layer. If temperature is higher than 22 Celsius degree, it will show highly absorptive for the infrared radiation. The absorption will also be amplified by photonic resonance with agency blocks and the silver layer. So for TARC, at high temperature, it will show strong radiative cooling operation mode, and at low temperature, it will show solar heating mode. So there are a lot of current problems for the past research, which is because they normally use the materials with fixed cooling optimized properties that will cause overcooling problems, and also some attempts are trying to switch off this kind of overcooling. But they normally require additional energy input and or external activation. So here comes of TARC's function here. Compared with other roof coatings, the simulations about space condition source energy savings show that the TARC will be more energy saving than any other roof coatings, which can be very alternative for the sky window coatings.
Well, speaking of more applications, smart textiles that can keep you at appropriate temperature are nothing new. However, these textiles also have other disadvantages. They can be large, heavy, fragile, and expensive. Many require external power sources. Guoming and colleagues solve this problem by starting with the fiber microstructure. Just like in the picture, the fabricated coating in this paper can also solve this problem. Find a way to apply it to the surface of fabric, so that the textiles can get the ability to adjust the temperature. With the development of science and technology, the performance of electronic devices such as mobile phones and computers is improving rapidly. High performance brings high heat production, while high temperature will cause performance decline. Therefore, temperature control is extremely important. Taking mobile phones as examples, most mobile phones in the market use liquid cooling or air cooling heat dissipation, which is not stable and will occupy a large space of the inner structure, reducing the user experience. This problem can be solved to a great extent if the fabricated coating in this paper is applied to the surface of mobile phones to improve its thermal emissivity at high temperature. Maria Brogren and colleagues found that titanium aluminum nitride coatings for satellite temperature control is a significant choice. The pictures are the representation and their samples, which turns out to be a great success, but still not suitable for different temperature range. If the coating design ideas in this paper can be applied to the aerospace thermal control coatings and make them temperature adaptive, it can extend the surface life of aerospace equipment and work stably. So, in conclusion, this paper introduces a kind of TARC, intelligent home temperature regulation, with mechanical flexibility and no energy consumption. Our system combines the thermally driven metal insulator transition with photon resonance. These attractive characteristics allow the system to switch from high-temperature radiant cooling mode to low-temperature solar heating mode, or insulation mode in outdoor environments. In most US cities, our simulations suggest that TARC may be superior to all conventional roofing materials at reducing household energy consumption. In addition, we also predict its future application, and the application prospect is fabulous. And thanks everyone for listening.